You should be able to just open the recordings. Now, I don't have a Mac, but you should be able to just open the recordings in any software that'll play video. So I think I use Microsoft Video or whatever it is, but you should just be able to. So I'm sure if you Google open video file, you'll find how you're supposed to open it. So we started talking about temperature. So that's what the first ever iClicker question is going to be on. And remember, we're on B8, so you have to be on B8. I try to put the words really big so everyone can see it. If it's ever to where you can't see it, just let me know. But I try to be aware of it. And you typically get 45 seconds, but if it's a math-related problem, I'll often give you a little bit longer. So on our temperature scale, this is a schematic of Fahrenheit, Celsius, and Kelvin. And of course, in the lab, we're typically looking at Celsius, but for calculation reasons, oftentimes we're looking at Kelvin. So we'll be using Kelvin a lot in the calculations. But because, of course, we live in America, we do a lot with Fahrenheit in everyday life, so it's good to understand how these correlate. And you can see that our 0 degrees Celsius in our Celsius scale, where water freezes, 100 degrees is where water boils. Our 0 degrees Celsius in the Fahrenheit scale is much lower, so you can see that correlation. The Kelvin scale is pretty easy. What you can see is that at 0 degrees, we're at 273 Kelvin. And that makes the conversion from Celsius to Kelvin quite easy. But it's not as easy necessarily to go from Fahrenheit to Celsius. Though we see that correlation. Now remember, 0 on the Kelvin scale is absolute 0. So the useful thing about using Kelvin is that we won't get a negative temperature. But if we're using Celsius and Fahrenheit, we can assume we can get a negative temperature because, of course, if 0 degrees is where water freezes in Celsius and 32 degrees is Fahrenheit, you can imagine room temperature for Celsius is actually somewhere around 27, which is not this room. It's a little bit lower. This room is cold. And at around 27, clearly if you're somewhere up north and it snows, you can imagine that the temperature is going to be below 0 there. And that's often happening in places where it gets fairly cold easily up north. So we have that negative number. And when we talk about gases, we'll see an equation where temperature is the denominator. So having a 0 in that denominator isn't really useful because you can't have a 0 in the denominator. So Kelvin will be necessary because absolute 0 is just not something realistically that we can survive. So it's not something that we usually look at. So we'll often use the Kelvin scale, and that's why it's our SI unit. So a Celsius degree is 1.8 times larger than our Fahrenheit degree, and therefore we can utilize that for our conversion. Now you should know this equation. You don't need to memorize the Fahrenheit to Celsius equation, because all you have to do is rearrange this if you're doing it. So you only really need to know one equation. And you see we're related to that number 32 here, and also that 1.8. So our degrees Celsius is equal to our degrees Fahrenheit minus 32 divided by 1.8. And we'll have to use that conversion if, for instance, for some weird reason, we have a Fahrenheit thermometer in the lab. And we have a couple in the organic lab, but we try not to use them because who wants to do this? But you'll have to do this in the test. So that's our calculation. Now, if we go from Celsius to Kelvin, however, it's fairly straightforward. Our Kelvin is just our degrees Celsius plus 273.15. And we typically don't really consider Kelvin a degree. Technically, we don't call them divisions degrees. We just call them Kelvin. So you won't often see the little degree sign when we're talking about Kelvin. And that's just a technicality that's used, and you'll see it throughout science. But Celsius and Fahrenheit, we do call the divisions degrees. This conversion factor you should know, and we'll talk about our units and our decimal places later. So do know 273.15, though oftentimes someone will be a little lazy and just use 273. But we're going to look in significant figures in this chapter in some details. So we're going to discuss that a little bit more. So looking at this example, this is going to be a pretty simple example, but I'm going to go through it. We have 0.0 degrees Fahrenheit, and we want to convert that to Kelvin. Now remember, we can't just add 273.15 because this is not Celsius, this is degrees Fahrenheit. So we'll first have to convert it to degrees Celsius, and then we can easily convert it to Kelvin. Like I said, you don't necessarily, technically you could look up the equation to have degrees Fahrenheit to degrees Celsius, but why memorize more things than you have to? You can just easily only know one equation and then convert it. So we do know that our degrees Celsius is equal to our degrees Fahrenheit minus 32 divided by 1.8. So we can use this equation. We can either rearrange it first, or we can plug in our degrees, and we don't need a rearrangement now. But if we were taking degrees Celsius to Fahrenheit, we could still use the same equation and rearrange it. We also know that our Kelvin is equal to our degrees Celsius. I don't know why I put my degree sign so small. Degrees Celsius plus our 273.15. So we can convert it to degrees Celsius and then convert to Kelvin. So converting to our degrees Celsius, we're given that our degrees Fahrenheit is 0.0. Minus 32 divided by 1.8. This is going to give us a negative temperature, and that's fine because it's degrees Celsius, and that's common. Now we're going to discuss taking significant figures over in calculations in the next couple of slides in this chapter, so we're not really going to talk about the decimal places too much right now. So we have our degrees Celsius. Now that we know our degrees Celsius, we can then convert to Kelvin. And I'm just going to put it in parentheses because it has that negative number attached. I'll often do this just so you don't lose a negative number or get confused when you are doing a calculation and using an equation. So now all we have to do is the simple addition to get our Kelvin temperature, which is 255.37. Notice some things I did. I kept degrees Fahrenheit and degrees Celsius here so I don't get lost when I'm checking my work of where those numbers came from. That's just some little tips that can help you. I will, when I'm grading, it's going to be multiple choice. Everything in here is multiple choice. But I will only give you partial credit for a math problem. I will be grading that your work is shown. So you need to make sure that you show your work in a way that I can follow it. And that's really useful to you because it's easier to check your work if you're writing it in a way that it's easily followed. And that will maybe not so much be important right now when we're doing something that's more simple. But when we get to things that are more complicated in math that's a little bit longer, it's going to be really useful if you can follow your work because then you can see where you made a mistake really easily, if you made a mistake. So it's a lot easier to follow. And when I do work on the board, sometimes if you know what you're doing, it might seem a little tedious, but I want to be really clear for everyone in the room that I'm showing all the steps clearly. For me, math comes fairly easily, so I want to make sure that I'm explaining it in a way that everyone can understand and I'm being as thorough as possible. So just bear with me if you're also someone like me who math comes easy. I'm teaching for everyone in the room, and I want to make sure when you look back at these notes, you can follow the math as simple as possible. Because we will be getting to things that are way more complicated than this. This is still fairly simple. I don't know why it keeps on doing that. I don't know why it keeps on taking what I drew and bringing it to the next page. I think they updated the system and it's doing weird things for me. It doesn't usually do that. So looking at this example, we're comparing Celsius and Kelvin. And the question is, first off, which object has the most kinetic energy? And then I put in parentheses highest temperature. That's one thing that's important. Our kinetic energy, our molecules will move more at higher temperatures. So we will see a higher kinetic energy at higher temperatures. But we can't compare degrees Celsius and Kelvin. We have to convert. It's irrelevant, really, if we're converting Kelvin to Celsius or we're converting Celsius to Kelvin. But if we're comparing these four things, the other thing that's irrelevant are what they are. We're just looking at the temperatures. What we need to do is have them in like units. So we need to convert Celsius to Kelvin, or vice versa, we can convert Kelvin to Celsius. So that way it can be directly comparable. I mean, we can see pretty clearly that C is higher than D, and we can see pretty clearly that B is a higher temperature than A. But it's really hard to compare these two unless if we actually do the conversion. So you don't necessarily always have to write this down, but we want to be able to convert these. And like I said, this is going Celsius to Kelvin, and we know that our Kelvin is equal to our degrees Celsius plus our 273.15. So we can do that conversion fairly simply. So if I do this simple addition, because for these it's pretty simple, we see that for A we would have 293.15 Kelvin, and that's fairly, and we already knew we could figure out that B is going to be higher in temperature than A. But again, for me to be thorough right now, I'm showing that one as well. And then if we look at B, and we add our 273.15 to 80 degrees Celsius, we have 353.15 Kelvin. So we can clearly see now that we're all in the same units, that B is going to be our highest temperature. And again, I showed this all converting to Kelvin, and oftentimes there'll be multiple ways or you can work things out. I recommend that if you're like, what if I convert this to Celsius? Do it, and you'll see that the answer is still the same, as long as you're doing it correctly. So that's perfectly fine, and when you're going through the notes, you could try other ways to work it out. Now, relating to our system, as we talked about our standard units, grams are great. Our kilograms are going to be our standard unit for mass. However, if I'm working in the lab and I'm doing something on a small scale, I won't be measuring out compound in kilograms. Kilograms is pretty big. So oftentimes what I'll be using is something more along the lines of grams or milligrams, or even micrograms. Oftentimes in biology, we'll be using microgram scales of things. But that's still going to be our mass. So we need to be able to convert with those sizes of the same unit. And that'll really help us out. So our standard units system are related by a power of 10. And we call and this is usually indicated by what we call a prefix multiplier. 10 to whatever, 10 to 6, which is just 10 raised to the 6th power. They're always the same regardless of what unit we're using. Meaning, a milligram is related to a microgram in the same way a milliliter is related to a microliter. And that same power difference. Even though one we're talking about mass and the other one we're talking about volume. So you do need to know these multipliers. And we'll typically report measurements in a unit that's closer to size. As I was talking in the last class that you might have a blood panel done at the doctor. And if you look at your blood panel, you might see that some things in your blood panel are measured in a certain size unit, like microgram, whereas some are more in milligrams. And that's because of what concentration it's supposed to be in your blood. And you need to be able to do these conversions and recognize them. So first I'm going to talk a little bit how to use this, but I want you to know from mega to micro. If for some reason you have to use nano or pico, I'll give you that one. Those aren't going to be as common for what we'll be discussing in chemistry. But especially kilo, deca, deci, centa, milli, and micro are very used. Mega, maybe not as much, it's pretty big, but those are used. So you need to know these. Like I said, if I want you to go from miles to kilograms, I'll give you that conversion, but these you need to know. Most of them will be using so much, you're not really memorizing them because we'll be using them and you just know them after a while. Secondly, let's talk a little bit about how this is set up. What this is saying is, this is our basic unit, let's say it's grams. So what this is saying is, this is my multiplier. So I have 1,000 grams in a kilogram. See this multiplier? 1,000 times 1. I have 1,000 grams in 1 kilogram. Remember, everything this way is big. So that'll help you remember these. And what this also means is I have 0.001 grams in a milligram, because a milligram is small. I don't like thinking in 0.001 terms, so what I'll say is I have 1,000 milligrams in a gram, because milligrams are small. And you can do that, because remember, this is just the multiplier. So this is saying your base unit, if you multiply by that number, that's how much you have of your base unit in that one of those. You don't necessarily need to memorize it from this table. I've looked up a bunch of tables and they're all sort of confusing like this. But this table will help you to remember that deca, kilo, hecta, mega. Mega is pretty straightforward. They're all bigger than your base unit. And deci, centa, milli, and micro, those are all smaller than your base unit. So you have more decis in one. So deci is 10. That's pretty common that terminology is used. Centi, I think from the time you were pretty young, you've known that means 100. So those things are pretty easy to remember. And then deca, again, that's 10, but that's going to be above. So that's how you use it. Personally, for me, again, I like thinking that I have 1,000 milligrams in 1 gram, but it's just as true to say that I have 0.001 grams in 1 milligram. And when we talk about conversions, both of those will work. Again, I'll typically stick with 1,000 milligrams equals 1 gram, but you're more than welcome to try it the other way. You should get the same answer. And if you do it that way on an exam, that's fine. I'll probably still teach it the other way, but I'm not going to take off because you're working it slightly different than I do. As long as you're still getting the same concept and really you're understanding what you're doing. There are often multiple ways that you can work through things. I typically try to teach the easiest method to think about it, but that doesn't mean that everyone's brain works exactly the same. So you have to memorize what's highlighted. And this is our multiplier, this 10 to the 6th. So that just means that we have 6 zeros. And now I know a couple of you probably know, okay, I write it down in a line and I move the decimal place however many times. And that's fine, but I'm going to teach you using our unit conversion method of converting because it'll make more sense when we start putting conversions factors together later on in this chapter. But I'm not teaching that method of moving the decimal place however many numbers. I'm not teaching that. So what our table says is, again, sticking with grams and looking at milligram. What this table says is, for 1 milligram, that equals 0.001 grams. Or, conversely, I can say 1,000 milligrams equals a gram. It means the same thing. Now, what isn't correct is for me to say 1,000 grams equal a milligram. Milligram is smaller, we always have more grams. So don't confuse that. Always remember what's smaller. Your milligram is smaller. So this is how I'm going to teach you with conversions, because it's going to go along with unit analysis throughout this entire class. So this is the way I'm going to teach it. So what I can say with this is, I can say 1,000 milligrams over 1 gram, or 1 gram over 1,000 milligrams. So if I'm starting with something in the units of grams, then I just choose this one because I want my desired units to cancel out. What happens if you divide 20 divided by 20? You get 1. So if you divide a given unit by a given unit, you get 1. And that's our unit conversion, and we'll be using that a lot. And I really, really recommend, even though these are simple, to write your units. Because when our unit analysis gets more difficult as we go through examples in chemistry and learn our theory, it's going to be really easy to lose your math because you left out units. So even though writing units takes a little while, you really can't ever go wrong if you follow your units. You can find where you've gone wrong. So if I started with 10 milligrams, I would use this and put milligrams on the bottom, and it cancels out. And I can do conversions really easily in that way. And I'll show an example. So let's say I do start with 5 milligrams. And I want to convert that to our grams. So I already know my conversions, my unit conversions. And I like to use this little method, but you don't necessarily have to. Call that my chicken wire, but you don't have to necessarily put it that way. I just find that it makes it really easy for me to know what's on top and bottom when I separate it this way. So I want my milligrams on the bottom. I know that 1,000 milligrams equals 1 gram, so I can put my 1,000 milligrams on the bottom. And they're going to cancel out because milligram divided by a milligram equals 1. And my 5 grams on the top. 5 grams, I'm so sorry. My 1 gram on the top, because 1,000 milligrams equals to 1 gram. And that'll give me my answer in my desired unit, in this case, which is grams. So always write your units. Now what if instead I use this? 1 milligram equals to 0.001 grams. I'm going to do the same thing. Same thing. Start with my 5 grams. There's my 5 milligrams. If I'm using this one, let's use blue so we could follow it later. I'm still going to put my milligram on the bottom, but I'm using the this relationship, which is exactly the same. So my milligrams still on the bottom. The 1 is with my milligram on that side of the equal sign, so that's what's still tied to it. And what happens? I get the same number. So either one you can use for conversions. There's no difference. That's the same answer. Typically, again, I like thinking this way. I find I make less mistakes. But if you want to use this, it means the exact same thing. And they're going to give you the same answer. So we call that conversion analysis. And we're going to be looking at this even more later on. Because really, as long as we have a relationship, and throughout the class we're going to see that, as long as we have a relationship, we can do unit analysis. We can do this multiple times in a row as long as we have relationships that agree. And we're going to look at that a bit more at the end of the chapter when we're going to look at a couple of example word problems. For example, we might convert something from our feet to inches or something like that. So we can use that as long as we have a relationship. And then when we start talking about chemistry, we'll be using those relationships to calculate things like theoretical yield. We'll be using those relationships to calculate how much mass of a certain atom we have in a molecule if we do a combustion reaction. So we'll be applying these concepts to chemistry. Right now we're just kind of talking about the concepts. So volume is actually a derived unit because it is based on our length, width, and height. So it's a combination of other units. Mass per, it's a measurement of the amount of space occupied. So any length unit cubed. SI unit is going to be our cubic meter. That's going to be our SI unit. Commonly though, a lot of times you see cubic centimeters. So 1 meter cubed equals 10 to the 6 centimeters cubed. And we have that relationship. And this is just drawn out. So it is a centimeters cubed. Now, we can't relate 1 meter directly to a centimeter cubed. We can relate a meter cubed to a centimeter cubed. That's an important concept. We would have to cube a meter first before we can relate it, because a meter and a meter cubed is not the same unit. Again, following your units will help you with this. And if you're not drawing your units, you might get lost. And it'll be a lot easier to not make a mistake if you're doing this. So also, in the liquid or gas volume, oftentimes you'll see milliliters. And here's just some conversions. Again, you don't necessarily need to memorize it. However, do know this one. 1 milliliter equals to 1 centimeters cubed. Because you'll see that oftentimes with density, where that's interchangeable. And it's interchangeable because they're equal. So 1 milliliter equals 1 centimeter cubed. Yes?
Is that also equal to 1 gram?
I need to recheck that conversion. No, that depends on density. We're going to talk about that. So it's equal to 1 gram of water because water's density, but not all things. So you're going a little bit ahead with mass. We're going to relate mass and volume. We're not quite there. And the next slide, I think, actually. So do know this one because you're going to see it often. So just know it's interchangeable. Oftentimes it will be shown, especially, and we're going to get to it in a second, in density. A lot of times density will be specified as milliliters or centimeters cubed, and it's the same thing. So we're going to look at that. Otherwise, you don't necessarily need to, and you can always, as long as you know your conversions for your SI units, you can figure these things out. Length is typically, here's some conversions. Again, you don't have to memorize these. If I ask you to convert inch to centimeters, I would give you these conversions. But we have relationships. So the way I did those relationships earlier with gram and milligram, we can also use these as long as we have a relationship to convert. And here's some common units in mass and volume. Again, you don't have to memorize these other than the typical liters and milliliters like we talked about before. But if I ask, though a lot of you probably know how many liters are in a gallon, if I do ask you to do a conversion with that, I will give it. So now we're getting there. Mass and volume. Two main physical properties of matter are mass and volume. Mass and volume are both extensive properties, which means the value depends on the quantity of matter. The more matter I have, that changes how much mass I have. The more volume I have, that changes how much volume I have. That's what it means in extensive. The boiling point won't change if it's a pure substance, but our mass and volume is dependent. So extensive properties can't be used to identify. If I have 1 gram of white powder, the fact that I have 1 gram of it tells me nothing about what it is. All I know is how much I have. So that's what we mean by it can't be used to determine what it is. If I have a large glass and my liquid is clear and colorless, and a small glass containing a clear and colorless liquid, are they the same? I don't know. There's no way that mass is going to tell me if they're the same. There's more things I need to do to determine if those two samples are the same thing. but our mass isn't going to be. I can tell you that I have a different amount of one than the other, but that's all I can tell you. So that's what we call an extensive property. It's dependent on the quantity of the matter. They are typically related to each other, and we will relate mass and volume in a couple of slides. I don't know why it stopped. Hold on. I don't know what it's doing. Okay. I'm sorry, it's giving me issues. It's not counting down, and I don't know why. So I just told you what an extensive property is, but this is asking about another type of property, an intensive property. And remember, you can change your answer as long as this is going. But now it's stopped. And I don't know why it's not showing the countdown time. And I will get the last answer that you sent to me. Now, density, which is the ratio of mass and volume of a substance, is an intensive property. It's independent of the amount of substance. The density of water is always the density of water, assuming we're at the same temperature. Because remember, at different temperatures, our molecules have a different kinetic energy. So we have to have that same temperature when we're discussing this. But it's independent of the amount of substance. I can have a gallon of water at this temperature and its density is going to be whatever it is, and we're going to talk about what it is. Or I can have, assuming it's a pure sample of water, a pool of water, an Olympic-sized pool. Assuming it's pure water, it's going to have the same density. So that's what an intensive property is, a value that's independent of the amount of the substance. So density is the same whether you have a gram or a kilogram. Our density is how our mass and volume relates. And our density is just our mass divided by our volume. And we're going to talk about common units for that as well. So for solids, typically you look at grams per centimeters cubed, or like I said, centimeters cubed are equal to milliliters. So you might look up the density and you might see grams per centimeters cubed. You also might see grams per milliliter. So that tells us that that's how our mass and our volume are related. In liquids, typically we're seeing grams per milliliter. Again, remember, centimeters cubed and milliliters are equal. And in gases, what we usually see is grams per liter. And when we talk about the gas chapter, we're going to look at that in a lot more because when we talk about density of gases. And oftentimes, we'll determine the density of a solid by having a volume of liquid, typically water, and measuring the amount of the water, the amount the water is displaced. That way we can figure out our volume. Because if we know the density, then we have a conversion factor. Typically, solids are more dense than liquids than gases. The exception is liquid water. Ice is actually less dense than water. And when you put ice in water, it floats. But most times, your solid is going to be the most dense, then your liquid, and then your gases, because you have less interactions, and your molecules aren't really interacting with each other, they're going to have the least density. Now remember, the density changes when our states change, even though it's the same substance, because we have a different amount of kinetic energy. because of molecular movements. So remember, at higher temperatures, we have more movement. So looking at this one, which of the following would not be considered intensive? The volume. Because volume can change with how much you have. And we'll actually look at, for example, these metals are typically shiny when they're in a solid state, things like that. So that actually does count as an intensive property. Melting, and when it's a solid, and of course the density, those are all intensive. That's not dependent on the amount you have. So now we're going to talk about actually utilizing and determining density. And I'm going to give you a few more seconds for this. Stop. Okay, I'm going to stop it because I don't know why it's doing that. I'm going to start it and give you a little bit more than 45 seconds so you can think about some of these actual numbers. Now I'm on the wrong one. I'm going to stop it again. I think they updated the word. It's not supposed to change when I move the mouse. Isn't technology fun? It really doesn't want you guys to answer this question, and it's not that hard of an eye clicker question. I got it. All right. Here it is. We were getting here. So our density, again, is related by mass and volume. So if we know the mass, we know the volume, we can calculate the density, because it's just mass divided by volume. Remember, your test will be multiple choice, quizzes will be multiple choice, so you do want to make sure that you have the right units of mass and volume that agree with whatever my multiple choice answers have. That's one little trick with multiple choice. Or if I specify I want it in grams per milliliter, things like that. So here are some densities, common densities. For certain substances, again, 20 degrees Celsius, because if we're comparing, we want to know what temperature we're at, because of the difference in kinetic energy. But for equal volumes, the denser object usually has a larger mass, because again, we can relate mass, volume, and density, and this is how we relate it. So heating an object causes it to expand. It has more kinetic energy. Therefore, the density does change with temperature. And you don't really have to memorize any of these densities, except for the fact that in most cases, we'll be thinking about water as 1.00 grams per milliliter, or grams per centimeters cubed. Now remember, ice is going to have a different density, but in general, in chemistry, for the temperatures we're working with, this is usually the density of water we'll be considering. Any other density, I will give you the density if it's something that I want you to know, or I'll give you information to be calculated. But most chemists always know density of water is 1. So let's look at an example. So if I say I want to know what this ring is, and I know how much of it I have its mass, and I want to know if it is a certain metal. Well, if I know And we're going to assume that we measured these things at a temperature that is in agreement with this. So if I have a list of densities of common materials, and I look at platinum, and I know that at 20 degrees Celsius, my density of platinum is 21.4 grams per centimeters cubed, then can I determine if this ring is platinum? And the answer is yes, because I can calculate the density of the unknown ring, or the ring of unknown material that I have, because I'm giving these. And again, remember, for it to be relatable, our density that we calculate has to be in the same units. So write down your units so you don't make a mistake. So this is grams per centimeters cubed, so that's what I want these units to be in. Nicely enough, I don't have to do any conversions, because I already have it in my mass in grams and my volume in centimeters cubed. So I don't really have to do any further work there. But if it wouldn't be, I would have to do a conversion. So is this ring platinum? We can set this up pretty easily by first finding the density of our unknown substance, our unknown ring. So we're given that our mass is equal to 3.15 grams. And again, I'm writing grams so I don't get confused. And my volume is 0.233 centimeters cubed. So to find my density, I know my density is related by mass over volume. I have both of those, so I will calculate it. My density of my unknown is going to be equal to my mass of my unknown divided by my volume of my unknown, which in this case is equal to 3.15 grams divided by 0.233 centimeters cubed. Not necessarily hard math. And you should always have a calculator, especially on tests or quizzes. And since you don't know when quizzes are, I always recommend you bringing one. Though this one you could technically calculate without a calculator, but why give yourself more work? So that's 13.5 grams per centimeters cubed. So the question is this platinum? If this was platinum, this density would be 21.4 grams per centimeters cubed. So it is very unlikely, since this does not equal to 21.4 grams per centimeters cubed, that this is platinum. It may be a mixture. It's likely not mercury. So it may be a mixture of something, but we can't really know any further than the fact that it's not platinum. And we could probably assume it's not mercury because, you know, mercury kind of looks different at room temperature, meaning it's a liquid and very poisonous. So we can kind of cancel some things out just by that. But what we do know is this is likely not platinum. And that's what we can definitively say from that calculation. And typically to do those measurements, you'd probably do it more than once just to make sure you didn't make a mistake when calculating volume. So looking at this one, first off, we are not calculating into density. So that's one thing we need to do to be able to compare these. It's kind of irrelevant, solid, liquid, because we're just asking which has the greatest density. What we can do, however, is this is centimeters cubed, this is centimeters cubed, that's liters. So we can do a conversion from liters to centimeters cubed. Now you might say, well, I don't know that conversion, but you should know your conversion from liters to milliliters. And then you know 1 milliliter equals how many centimeters cubed. So you know that one already. B, you're just not calculated correctly because you're not actually shown the actual density, but we just showed how we could do that, which is 5 grams divided by 10 centimeters cubed. C is already calculated. Well, what you're saying is it sinks in ethanol. If it sinks, that means that your solid must have greater density than ethanol because it sinks. Remember, if something sinks, it has more density. If it floats on water, that means it must be less dense than 1. So your density is somewhere between, it's higher than 0.789, but lower than 1. So we don't know exactly what it is, but it's somewhere in between. So when you do all of those calculations, what you actually see is C is going to be the lower number. But you do have to do some conversions. Now they're all in grams per something, so we don't have to worry about changing the masses. But we do need them to be directly comparable if we are looking at them as comparable things. And I'll come back to working this one later on when we talk about conversions later in the chapter, and really reiterate actually doing these conversions. But we're going to talk about conversions more later in the chapter and really dissect how to do some conversions. Another example, let's look at this one. In this one, we have the density of brass, so we already know what the thing is, but we want to know what the density of it is. If we have a certain mass, which is given, and then we put it in a cylinder of water, and the water level changes. So how do we calculate this one? And this one's not specifying if we want it in grams per milliliter or grams per liter or grams per centimeters cubed. So we're just going to assume it's in grams per milliliter because that's what we have. So unless it's otherwise noted, we can make that assumption. So the question is, how do we work this one? Well, we know our mass. And remember, you can always start with your calculation. We know our density, which is what we're looking for. So we know our density is equal to mass over volume. We know our mass is given. Notice how I just copied that down wrong? Always double check yourself. I'm thinking ahead, so then I put my decimal place in the wrong place. Make sure what you're given and what you write is the same thing. Just a simple tip to not make simple mistakes in your math. Because oftentimes I'll see students doing everything correctly and making a simple mistake, what you might have noticed if you had looked over your work. So I'm thinking ahead in what I want to tell you, and then I wrote it down wrong. So watch out for that. We all do it. So just be careful. Now we don't have our volume, but what we do know is our volume of our water, our V1, started at 25.0 milliliters, and our V2 after we added our brass was at 36.9 milliliters. So our solid object displaced a certain amount of water, and that'll really give us our volume, especially if we have an object where it's not easy to measure length, width, and height. So this is a really common method. So all we have to do is, for our volume of our brass object, is our V2 minus our V1. And of course, we can't displace a negative amount of water. We're putting something in. We're going to displace it positive. So if you get a negative number, recheck what you did, because that's a pretty good indication based on what you know about life. Really, if you ever put something in water, can you get a negative amount? You can't. It's going to move it. So think about that. Use a little bit of common sense in some of these. And these are both in milliliters, so we don't have to worry about doing conversions. So when we do this calculation, we have 11.9 milliliters, and we're not being told if we want it in milliliters or centimeters cubed, but if we did want it in centimeters cubed, it would just be 11.9 centimeters cubed. So pay attention to what the question's asking. This one wasn't specific. So our density is equal to our mass over our volume. So that's going to be equal to our 100.0 grams divided by our 11.9 milliliters. Or since this is a solid, let's do it in centimeters cubed since that's our SI unit. But I'll be really specific on what I want because you have multiple choice. Bless you. So clearly, if all the units are in grams per milliliter on your multiple choice, that's what I want. When we do that calculation, and we're going to talk about our significant figures later on, probably on Monday, So we're not going to focus on that right now. And how many decimal places we should have. So right now I'm just putting all my decimal places. But we're going to get more specific on that. Grams per centimeters cubed. So fairly straightforward ways to calculate density. So we're going to start on significant figures and what it means on Monday. So start going over those, and we'll talk about why it's important. Sometimes it seems like it's just really annoying, but it is really important, and we'll talk about why, especially when we're talking about actual data from the lab. So y'all have a good weekend. Remember to keep up with Moodle just in case the weather turns. And be safe if it is raining on Monday when you drive in. Start that again. How are you?
I downloaded a few of those. I don't know. Okay.
Let me just stop this recording real quick because I don't want to record us talking and then put it in the notes.